Hey monkeyheads, I know this is a thorny issue for a lot of students, and I'm still kind of unsure the level that it will be represented on the new test, but I bet it's going to be there at least indirectly. So for some additional support, I want to go back over the slides that I did in class on predicting products. So let's dive in. Alright, first topic I want to cover is synthesis, and what you'll be looking for in synthesis is basically two or more things become one product. Your reactants are probably going to be single elements. You're going to have a metal and then some non-metal, probably one of these guys, sulfur, oxygen, or a halogen gas. Basically, you're going to be starting from the single elements and making an ionic compound. So you got to have something that's a metal and something that's a non-metal. So, as I said, the key thing about synthesis reactions, one product. And so you're going to take whatever the two single elements are, you're going to figure out what charges that they have as ions, and you're going to make a neutral compound out of them. So that's what I mean by charge balancing. Taking two opposite charges, finding how many of each you need to make a neutral compound. That will let you get your products, and then you're going to tack those on the other side of the yield arrow and balance your overall reaction. So let's look at a couple examples. Okay, so if you were shown this, cesium plus sulfur, what you've got here is you've got two single elements, check. We've got a metal, that would be the cesium, and we've got a non-metal, that would be the sulfur. So those are your clues that this is going to be synthesis. And again, we're going to be making one product, metal sulfide, and we can consult the periodic table and find that cesium will be +1, it's an alkali metal, and sulfur will be -2, it's a chalcogen. And the way that I did when I wrote this is finding the least common multiple of the two charges and then making a neutral compound that way. Since you guys are a little swifter than most of my chem students, I want to show you a quick and dirty way, and that's just to crisscross your charges. I don't do this for my Gen Chem classes because there are some pitfalls out there, but if you're careful, this is a really quick way to do it. So we've got cesium, and it's a plus, and sulfur, it's a 2-. You're just going to take whatever your charge value is, and that's going to become the subscript on the other thing. And the key thing that you need to remember, which is why I don't tell this to my Gen Kid chems, can't say that, Gen Chem kids, is to always remember to simplify. And of course we're naturally taking like the absolute value of the charge. You're not going to have -2 cesium atoms. So you swap those out, you get a 2 here, you get a 1 there. That's already a simple whole number ratio, and so that's our product. CS2S. So I want to stick with this method from here on out because it's really quick, and I don't have to rehash like what's the least common multiple of 2 and 1 sort of thing. So this is our product. Tack it on the other side of the yield arrow, and then look for anything that's not balanced. I've got 2 cesiums, so I've got to come over here and put a coefficient of 2 on this, and there we go. Done and done. Let's look at another one. Alright, similar game here. 2 single elements. Even though one of them, this is still an element, even though it's a member of Brinkelhoff, that's why it's 2. It's always really important to remember our Brinkelhoff on things, especially when we get to writing products. That'll come back later. And we've got a metal and a non-metal, and so that's our tip-offs for synthesis. So making one thing, barium oxide. We've got 2+ because barium's an alkali earth metal, and oxygen is another chalcogen, so -2. And so if I did my crisscross method on this, we would get Ba2O2, and this is where you have to remember to simplify. You wouldn't turn into your math teacher 2/2, so we're not going to say barium 2, oxygen 2. We're just going to simplify that to BaO. And we put that on the end. Look for anything that's not balanced. Because oxygen is a member of Brinkelhoff, it's plus O2. So I'm going to need to make a coefficient of 2 here to get my 2 oxygens. That also makes me have 2 bariums. So 2 bariums. Beryllium plus chlorine gas. Same game as before. We've got a metal and we've got a non-metal. We're going to be making beryllium chloride. Beryllium, alkali earth metal, plus 2. Chlorine, halogen, minus 1. Crisscross. 2 goes to the chlorine, 1 goes to the Be. It's already simple. And we put that there, and this one's balanced as written. And so I think that is synthesis for you. Decomposition. This one is the worst one of the lot because there is no consistent way for things to decompose. Your tip-off will be that you have one reactant, and it's going to have some polyatomic ion in it. And that's really the only thing that's common across all the decomposition reactions, is that you have a polyatomic ion, and in some way that polyatomic ion is going to decompose or break apart. The ones that you're likely going to see are a metal carbonate, so CO3 2 minus as your polyatomic ion, metal hydroxide, OH1 minus, or metal chlorate, where chlorate is ClO3 1 minus. The other thing that you may be decomposing is an oxyacid, and that is a polyatomic ion that has had hydrogens added to it. These are going to decompose into most likely 2 products, and this is why this reaction type sucks, because there isn't much consistency here. Carbonate, you're going to split the carbonate into an oxygen that will stay with your metal and CO2. The hydroxide, a couple of hydroxide ions are going to team up. Some of the oxygens are going to stay with the metal. Some of the oxygens and the hydrogens are going to form water. Chlorates are going to split up. The chlorine is going to stay with the metal, and the oxygen is going to come off as oxygen gas. And oxyacids, basically you're going to look for whatever the nonmetal is in the polyatomic ion, it's going to form its oxide. Hopefully it's something that you would recognize, like carbon dioxide or sulfur dioxide is the oxide that you're forming. And that's going to be formed by what we would call dewatering, removing the hydrogens that are added to the polyatomic ion and one of the oxygens to make water. And it may be necessary to get it to balance to evolve some hydrogen gas too, remembering that hydrogen is a member of Brinkelhoff. So when we kick any of those out, they have to be H2. And you're going to balance it. So let's look at a couple examples. Alright, what we've got here, one reactant, so that's how we know for certain it's a decomp, and it fits one of our descriptions. It's a metal carbonate. So within this, I'm going to split my carbonate up into CO2, and some of the oxygens are going to stay with the metal. Alright, now this is the first thing that we've come across here in the class so far, where we have a member of the transition metals involved. And you don't automatically know what the charge on the transition metal is. But what you will know is the charge on the ion. Either it will be something like a halogen or a chalcogen, where you can get its charge from its location on the periodic table, or in this case, a familiar polyatomic ion. Anytime you're dealing with a transition metal and you need to determine its charge, here's a little mental math that you're going to do. You're going to have your number of ions times the absolute value of the number of anions times the absolute value of the anion over number of cations. And that's going to get you your cations charge. So in this case, we had to look at this and say, okay, I've got two carbonates. Each of those is a -2 charge, and that's being balanced by one manganese. Therefore, manganese is +4. Okay. The previous slide just said that we're going to make manganese oxide. Oxygen we know to be -2, so we're going to do the crisscross trick here. The 4 goes to the oxygen, the 2 goes to the manganese, and you simplify, so you get manganese, MnO2. And our other product is just CO2, so we put those on the end of this reaction. There we are. We'll look for anything that's not balanced. I have 2 carbons because I have 2 carbonate ions, and so I've got to put 2 there, and that takes care of it. Alright, oh boy, we get to practice on our D blocks again. So I know that I have 5 hydroxides. Hopefully you know that hydroxide is a -1, and that's being balanced by 1 chromium. So chromium is a +5. My decomposition is that of hydroxide, so that splits into an oxygen, which goes with my chromium, so I need to charge balance +5 and 2 minus, so 5 goes to the O, 2 goes to the Cr. That's in lowest terms, so my product is Cr2O5 plus water. So put those on there. Look for anything that's not balanced. I have 2 Crs, so I put this guy there. That gives me 2 times 5 times 1 hydrogen, so that's a total of 10 hydrogens. So I need to make there be 10 hydrogens there. Alright, here we have a chlorate decomposition. I was merciful this time and just did an alkali earth metal, so there's no mystery to the charge of strontium. And in the decomposition of chlorate, we're going to make a metal chloride, so strontium chloride. 2 goes to the Cl, 1 goes to the Sr. That's in lowest terms. So there's my strontium chloride plus O2. Put that there. Look for anything that's not balanced. We have a total of 6 oxygens here, 2 times 3. So I need to make there be 6 oxygen atoms here, and we have that. Alright, here is a decomposition of an oxyacid. So there is a familiar polyatomic anion, the carbonate, and it's had hydrogens added to it. So this is an oxyacid, and we're going to try and remove water from this and leave us with some nonmetal oxide. So when I remove my water, so that's going to be these 2 H's and one of these O's to make water, that leaves me with 1 C and 2 oxygen remaining. So that's pretty convenient. So I feel comfortable with that because I know that that's a familiar oxide of carbon for me, CO2, carbon dioxide, plus the water that we just removed. So those are my products. There we are, and this one is balanced as written. Now I don't have a slide for this, but I do want to write out one of these where you'll have to have some excess hydrogen gas evolved. So let's decompose phosphorus acid. So if you saw this here, you'd recognize a polyatomic ion there. PO3 3- is phosphite, and we've added hydrogens to it. So I need to try and remove water. So when I remove water from this one, I want to take out 2 of these hydrogens and 1 of these waters, or 1 of these oxygens to make my water. And that's going to leave me with phosphorus dioxide, which I'm okay with that. The trouble is we still have 1 hydrogen remaining right here because we took 2 of those to make our water. And so I can't just have that guy hanging around. So in this case, I do have to have plus H2 to take care of the fact that I removed 2 of the hydrogens to make water, and I've still got 1 hydrogen hanging around. And of course I can't do just plus H. That would be really convenient and make my equation easy to balance, but since H is a member of Brinkelhoff, I'm going to have H2. So let's write this guy out and balance it. So there's the water I removed, there's my nonmetal oxide, and there is my excess hydrogen. So we have a total of 4 hydrogens over here. Everything else is balanced, so I'm going to have to fix that. So I'll have to put a 2 there. So now I have 6 hydrogens, and I have 2 phosphorus and 6 oxygens. So 2 phosphorus, that brings me up to 5 oxygens. So now I have 6 oxygens, and there's 4 plus 2, 6 hydrogens. So everything is now balanced. So didn't have a slide for that, but I did this one in class so that you would have an example of decomposing an acid where you have to have the plus H2. Oh, I did make a slide for that. Well, never mind. There we go. Forgot about that. Moving on. These are some problems that I assigned for homework if you weren't in class. So this is a mixture. Everything on this slide is a mixture of synthesis or decomp. And you can see me in class if you want a key. Alright, single displacement. This is like the drama of high school dance, because we're going to have one single element that comes to the dance by himself, and we're going to have a 2-part compound. And the person who comes stag is going to cause a breakup of our compound. And the one thing that you got to be careful with, chemistry is a very, very conservative science as far as these relationships go, and cations are always going to kick out other cations. So basically, our cations only want to dance with anions when we make a product, because we need the opposite charges there. So make sure that when you do any switching, you are switching it for the equivalent part, and whatever gets kicked out is a single element. Be on the lookout if you have to kick out a member of Brinkelhoff, that you make sure that you kick those things out as diatomic molecules. Otherwise, your problem is going to be wrong. One handy thing to think, a lot of single displacement reactions involve water. Students have a tendency to split water into 2 hydrogens and 1 oxygen. Water in single displacements is split as 1 hydrogen and 1 hydroxide anion. So remember to think of water like that, and charge balance it, balance your reaction. Okay, so speaking of water, that's what I gave to you, because that's a common thing to see, and a lot of students want to mess that up. So we've got a single element, magnesium, and a 2-part compound, water, and put a reminder there to think of water like that. So this is going to be the single displacement. I want to think about, okay, magnesium is a cation, so it is going to want to dance with the anion part of water, so the hydroxide. I do my crisscross. 2 goes to the hydroxide, 1 goes to the manganese. This might be new to you. Anytime that we need to make multiples of a polyatomic ion, we put it in parentheses. We don't expand that 2 and write this as MgO2H2, because then you might not recognize what the polyatomic ion is. So we go ahead and leave it in parentheses, and we're going to kick out the hydrogen. It's a member of Brinkelhoff, so I have to kick it out as H2. So products are magnesium hydroxide plus hydrogen gas. Only thing that isn't balanced is I have 4 hydrogens and 2 oxygens over here, and I can take care of that like so. Okay. Potassium plus calcium sulfate. So single element is potassium. Potassium is a +1 cation, alkali metal. So it's going to kick out the cation and dance with the sulfate. And sulfate's polyatomic ion with a -2 charge. So I need to crisscross those. 1 sulfate, 2 potassiums, K2SO4. And calcium, I'm fine kicking it out just as calcium. It isn't a member of Brinkelhoff, so I can just say plus Ca. And the only thing that is not balanced then is I have 2 potassiums in my product, so I need to put a 2 there. Double displacement, this is really just a slightly more elaborate single displacement where you're going to have 2 compounds and they're just going to switch their respective anion and cation parts. So, and if water is involved, remember to think of it as HOH. Alright, so we're going to look at this. I'm going to figure out the charges of everything. Sodium, alkali metal, +1. Calcium, alkali earth metal, +2. Phosphate, polyatomic ion, -3. Chlorine, halogen, -1. So now I'm ready to switch parts. So the sodium was with the phosphate, so I'm going to switch it with and pair it up with the chlorine. The calcium was with chlorine, so now I'm going to pair it with the phosphate. And so charge balance. 1 goes to the Cl, 1 goes to the Na, NaCl. 2 goes to the phosphate, put the phosphate in parentheses to show 2 of them. 3 goes to the calcium. Tack it on to the end of my equation. Look for something that isn't balanced. I have, let's see, what did I balance first on this? I think I balanced the fact that I had 3 CAs first, so I put 3 CAs here. That makes me have 6 chlorines, so I put a 6 there. That also gives me 6 sodiums, so I have to put a 2 there. Alright, gave you a D block in this, so calcium's alkali earth metal, it's +2. Chromate's polyatomic ion, it's -2. D block, but we do know that I have 3 sulfurs. They're 2 apiece, being balanced by 2, so Fe is 3+. So now I have my charges on everything, and we're going to switch the equivalent parts. Calcium was with chromate, so I'm going to pair it with sulfur. 2 goes to sulfur, 2 goes to Ca, simplify to CaS. Iron, 3 goes to chromate, put chromate in parentheses, 2 goes to Fe. And put that on there. The only thing that is not balanced is my sulfurs, so I put a 3 there, and then I come back and put a 3 there, and that takes care of everything. Ooh, acid base. Okay, first thing I need to do is introduce our definitions of acidity. Big, huge chunk of the course after Christmas we'll be dealing with acidity. We'll actually have 2 definitions for acidity, working today only with the Bronsted-Lowry definition. So Bronsted acids are protons, so that is H+, proton donors, so those will take the form of hydrogens added to halogens or polyatomic ions. We already mentioned the hydrogens with polyatomic ions when we did the decomposition. And if an acid is a proton donor, a base is a proton acceptor. So what you'll see for common bases are hydroxide paired with a metal, very likely to be alkali or alkali earth metals, or one of the few positively charged polyatomic ions. And you might get a hint of what we're making here. If we're having one thing that donates a proton to one thing with a hydroxide, we're going to be making water. So if our acid base is in the form of a double displacement reaction, we're going to be making a salt plus water. They can be in the form of a single displacement reaction where you just have an acid plus a metal, where the metal isn't a straight up base, it doesn't have hydroxide with it. Then we're going to get a single displacement reaction where you still make the salt, but instead of making water, because there's no hydroxide, you just get hydrogen gas. Let's look at an example here. Okay. Here is my proton with a halogen, so that's my acid. Here is my alkali metal with a hydroxide, so that is my base. And this one's going to be a double displacement because I've got compound, compound. So I'm going to be making a salt plus water. And you can probably see that. There's my H, there's my OH, so those are my parts for water. My salt then is going to be, well, salt, sodium chloride. So alkali metal, halogen, 1 and 1, crisscross, one goes to Cl, one goes to Na, and we've got NaCl. So put our salt in our water onto the reaction, and lo and behold, it is balanced already. Okay, this one takes the form of a single displacement reaction because there's my acid, hydrogen added to a polyatomic ion, and we have just a plain Jane metal. So not a base here because we're lacking hydroxide. So without a hydroxide, we're just going to have our salt plus the hydrogen gas which comes from our acid. So that tells us our salt must be calcium sulfate. Calcium, alkali earth metal, plus 2. Sulfate, polyatomic ion, minus 2. Crisscross, 2 goes to calcium, 2 goes to sulfate. Simplify, calcium sulfate. And then plus H2, remembering it's a member of Brinkelhoff. And once again, lucky us, we are balanced. Okay, last type, combustion. The easiest one to predict products for because there's no charge balancing involved. So I kind of like combustion. So what you will see at minimum, you will have a hydrocarbon, so something with carbon and hydrogen. Your hydrocarbon may include oxygen, nitrogen, and or sulfur, plus, and here's the key thing that makes a combustion, combustions need oxygen gas. So it's going to be carbon, hydrogen, something, maybe with these, plus O2. And this is why these reactions are cake, because their products are always, at minimum, carbon dioxide plus water. Optionally, if you've got nitrogen, you'll have NO2. And optionally, if you have sulfur, you'll have SO2. So no work to predict your products. So let's see what we've got here. Hydrocarbon. Whoopsie. Grabbed the wrong thing there. Lost my pointer. Hydrocarbon plus O2. So got a combustion. We don't have N or S, so our products are just carbon dioxide and water. So tack those on to the end. Balance. Alright, here we've got another combustion. Made this slightly more complicated because I dropped in an extra oxygen here. So we've got some ethanol plus oxygen. We know that burns. So C, H, and O plus oxygen gas, combustion. Products, again, no nitrogen, no sulfur, so it's just carbon dioxide and water. The only trick on these is students a lot of times fail to remember when they're balancing this that you've got some oxygen already in this. So let's look at this. 2 carbons, check. 5 hydrogens, or 6 hydrogens, 5 there, 1 there. It's like, wait a second. 6 hydrogens. Oh, did it again. 6 hydrogens. Oxygens. I've got 4 there, plus 1, 5 total oxygens. So on here, I have 1 oxygen already in my ethanol. So I only need to get 4 remaining oxygens, so I put a 2 there. That's the only hiccup that students have on some of the more complicated combustion reactions, is they forget that they may already have some oxygens outside of just the plus O2 gas. Ooh, here we go. Big one. Got everything in. We've got carbons, hydrogens, nitrogens, oxygens, sulfurs, plus O2 gas. So this one is going to have the full gamut of everything that you might see for a combustion product. CO2, H2O, NO2, SO2, everything. So tack all of those on. And again, the only hang up here that students have is when you balance your oxygens, you've already got some there, which is why we want to balance oxygens last. So 6 carbons, check. 12 hydrogens, check. 2 nitrogens, check. 2 sulfurs, check. Let's total up all the oxygens now that we have balanced everything else. We have, I'm going to write this down, I have 12 here, I have 6 here, I have 4 here, and I have 4 here. So we've got 18, 22, 26 total hydrogens. So a lot of students would say, oh, 26 oxygens, and they would slap a 13 on this O2 to get 26 oxygens, and that would be flat wrong, because they have failed to account for that they have 4 of the oxygens right there. So you only need to get 22 oxygens, so that's why correctly balancing it is 11. So combustions can be really easy because you have no work to do your products. Don't get thrown off by one of those guys. Alright, that is that. And again, I assign these. So these are a mix of single displacement, double displacement, acid-base, and combustion. So see me in class if you need a key for those. Have a good evening.